Alright, we're going to begin this video with a few of the patterns that we found in our lab. So if we look at circuits 5, 6, and 7, this is very similar to circuit number 6. Okay, in this video, I'm going to be using 8 volts for the battery. We have 3 light bulbs in parallel. We have 2 ohms, 4 ohms, and 8 ohms. Okay, so we're going to close the switch here. We see the simulation will light up and work. Alright, so if we look very carefully, a few patterns that are going to be really important to us. The first is, how does the voltage of the battery compare to the voltage of the light bulbs? So here we see here that the change in voltage across the battery is 8. We then go to each bulb. This is about 8 for the 2 ohms, about 8 for the 4 ohms, 7.99, and for the 8 ohm resistor is also 8. Okay, so one of the most important things here is that for a parallel circuit, the voltage going in to each part is going to be the same for each electrical component. In this case, the voltage going into the 2, 4, and 8 is 8 ohms, so the voltage across each one is 8 ohms. Alright, now, the second pattern that's extremely important is if I look at the current here and the current here. Notice if I go from the battery, all the current's in one path. Now here it splits once, and here it splits again. Each time it splits, okay, the total 7 amps splits into 4 and 3, and then again into 2 and 1. They all come back around. The 1 and the 2 meet up to make 3, and the 3 and the 4 meet up to then make 7. Alright, every time a current goes into a junction, okay, the sum of the currents going in is equal to the sum of the currents going out. This rule is known as the junction rule, and it's going to be extremely important in analyzing parallel circuits. Every single time you have wires that are connected that go off into multiple branches, or multiple branches of wires going into 1 or 2, the sum of the currents going in will equal the sum of the currents going out. We're going to use this rule along with the loop rule to analyze parallel circuits. Alright, so let's look at this. We have a parallel circuit of 3 resistors, R1, R2, and R3, 1 battery of delta V, and I put in 4 different, or 5 different ammeters. Alright, so what we're going to do, here's a little quick summary of what we just talked about. The junction rule is the sum of the currents, and I'm not quite sure why the extra E is there, so we'll take that out. The sum of the currents going into a junction is equal to the sum of the currents leaving the junction. And then the other key idea is the voltage for resistors in parallel. Electrical components in parallel will have the same voltage across each. So we have to keep this in mind when analyzing this circuit. And for this, we're going to come up with a derivation for resistors in parallel. Alright, so leaving the battery, we have our original current, our current for the whole circuit. We're just going to refer to this as I subscript 0, or I know. As it approaches this first one, the current will split into 2. We'll call this I3, and then this will be I1, 2, because it splits into 2 parts here. Here, that will split again. Across the top one will go I1, and across the middle will go I2. Alright, so this is essentially the junction rule. Junction rule is basically stating that at every junction, the current, whatever the value is, will split into 2 different currents that add up to equal the original value. Then it hits another junction, will split up again to 2 values that equal the original value. We come back to this side. Alright, we know that I1 comes back here, and I2 comes back into here. These two will combine, and then this will be that I1, I2, and I3 will come across and combine, and this will equal the original I0. Alright, so how to analyze resistors in parallel. Alright, we're going to start with the junction rule to analyze this. If we look at this, the junction rule basically states that I0 will equal I1, I2 plus I3. And then again, I1, I2 is equal to I1 plus I2. Or I can combine these two and say I0 is equal to I1 plus I2 plus I3. Either one is fair game, technically. This is more accurate than just stating that, but we're going to run with this anyways. Alright, now that being said, and for those of you who didn't see that, all I did was take these two values and substitute them in here. That's how I ended up with I1 plus I2 plus I3. Alright, so now that being said, we know the voltage across each resistor, delta V, is going to be the same. And in this case, it'll be the same as the battery. So I can use Ohm's law, change in voltage over R, to rewrite this whole expression. Alright, so I'm left with I0 will equal delta V over R1 plus delta V over R2 plus delta V over R3. Alright, now given that the change in voltage is the same, I can rewrite this whole thing as delta V. So essentially I'm factoring out the voltage is 1 over R1 plus 1 over R2 plus 1 over R3. Okay. And this will equal my current, I know. Now looking at this, right here, I have my equivalent resistance. So my equivalent resistance will equal 1 over R1 plus 1 over R2 plus 1 over R3. And to generalize this, as many resistors are in parallel. So the equivalent resistance in parallel will equal the summation of resistors, or 1 over the resistors in parallel. Now when you guys are doing this, as I'll get into the example problem, make sure you take the inverse before you find the actual equivalent resistance.